This is the model that we built in Module 6. So first thing you would want to do is save this model as Module 7, and then you want to run the Module 6 base so that later we can compare that with Module 7 base. Okay? So what we're going to do first is we're going to compare the hospital demand to hospital capacity. Okay? And that comparison will help the policymaker decide how much of the hospital capacity to be allocated for the COVID-19 patients. Okay? So in order to calculate that, the first step is to figure out how many of those infected symptomatic population will actually need a hospitalization. So we're going to create a variable called fraction of infected symptomatics needing hospitalization. So let's create that up here. Okay. So, and then we're going to multiply that with infected symptomatic population. And what that's going to give us is infected symptomatics needing hospitalization. So basically, this is the demand for the hospital. So we're going to create a arrow from here, and then arrow from the infected symptomatic population. Okay, so looks like this. Okay, so for the equation, the fraction of infected symptomatic needing hospitalization, let's just set it to 0.2. So basically we are assuming about 20% of the infected symptomatic population will require hospitalization. And then because this is a fraction, we're just going to set the unit as dimensionless. Click OK. Now the infected symptomatics needing hospitalization, the equation for that would be infected symptomatic population multiplied by fraction needing hospitalization, and then the unit's going to be same as infected symptomatic population, which would be person. Okay. All right. Now the next step is we're going to compare this with the hospital capacity, and even though in a normal situation we want hospital capacity to be a stock with inflow of building hospital capacity and outflow of demolishing or closing down hospitals, in this model, because we are running it for fairly short period of time, we're going to assume that the hospital capacity is fixed. Okay, so it doesn't really have inflow or outflow. There is a delay in building or expanding hospital capacity, so that is not going to be considered here, but we're going to use the level tool here and then say capacity. Oh, we're going to say hospital capacity. However, this one will actually stay constant. Okay, so when we do the equation, click that, and then it's just gonna be the type. We're gonna change it to constant. Okay, and then the value will be, we're gonna set it at 128,000. Okay, so that's gonna be our hospital capacity. And usually when we are talking about hospital capacity, we'll count it as number of beds. But because we're going to be comparing that with number of patients, I'm just going to use the unit persons. Okay, so we're going to assume that the capacity that we have can accommodate 128,000 people. Okay. All right. Now we're going to compare the demand with the capacity. So the variable that we're going to create is going to be called ratio of infected symptomatic needing hospitalization to hospital capacity. So basically we are comparing these two variables. Let me just create some more room here, right? So create arrows like this. And then basically the equation for this would be, in the numerator, we're going to have infected symptomatics needing hospitalization, and we're going to divide that by hospital capacity. Okay? Okay, so the unit, this one is persons, this one is persons, so, you know, it's a ratio, so unit's going to be dimensionless. And click OK. So how do we know this current demand to capacity ratio is more than what we can accommodate? Okay, so what we're going to do is now we're going to compare this ratio with normal situation. Okay, so that variable is going to be called normal fraction of hospital capacity. That can be allocated to infected symptomatics. Okay, so now we're going to compare this ratio with the normal rate, okay, normal fraction. So for now, let's set the value to 0.33. So we are saying about 1/3 of hospital capacity can be comfortably allocated to COVID-19 patients without putting much strain on the system. Okay, so in this case, the unit's going to be dimensionless. Okay, so now we're going to compare these two. Okay, and based on this comparison, we're going to make adjustment to how much of the hospital capacity will be allocated to COVID-19 patients. So that variable is going to be called adjustment made to the fraction of, okay, so this is the adjustment that we're going to be making. So we're going to use a table function, and that table function, we're going to call that F3. Okay, so input for that table function is comparison of these two, so we're going to be adding arrows like this. Okay, now let's define this adjustment multiplier. So click equation, okay, and you're going to click this, and it's going to use the table function F3, and then the input or x-axis of that table function is going to be the current ratio of infected symptomatics needing hospitalization to hospital capacity over the normal fraction. Okay, the unit's going to be dimensionless. Okay, now F3 is going to be a lookup function, so we change to lookup. Okay, so the equation is going to be, you click as graph, and let's first adjust the x and y maximum and minimum value. Okay, x maximum, we're going to just go from 0 to 2, and then y maximum of maybe 2 as well. Okay, now let's put in the points. Let's go from when this ratio equals the normal fraction. Okay, so then we don't want to make any adjustment to the fraction of hospital capacity allocated to COVID-19 patients. So this multiplier would be 1 because we are multiplying this number to the normal fraction. Okay, so we can add these points by clicking enter. Okay, so if this ratio is less than the normal fraction, okay, then what happens is there is no pressure in terms of hospital capacity. We have enough hospital capacity to accommodate everyone. So whatever this ratio is will be the actual fraction of hospital capacity allocated to COVID-19 patients. Okay, so we want to have a straight line here. Okay, it's a linear relationship. Okay, so we want to put like 0, 0. Okay, however, we want to make it slightly bigger than 0, like 0.01, just to avoid any calculation error when it comes to like division by 0. We want to avoid those situations, so it's kind of safe to put 0.01. And then when this ratio is, let's say, 50% more than the normal fraction, so in this case it would be 1.5, then let's say that we're gonna increase the hospital capacity allocated to COVID-19 patients by 20%. So let's say we multiply by 1.2. Okay, and then when this ratio is twice as much as the normal fraction, in this case 2, we're going to say here the multiplier will be 1.25, implying there will be 25% more hospital capacity allocated to COVID-19 patients. Okay, so what you can do here later on is, as a policy decision, you can change these values. So rather than increasing the allocation of hospital beds to COVID-19 patients by 25%, maybe you could go even further and say 1.5 or 2, or even, this input value might be more than 2, right? What if this ratio is 4 times more than the normal fraction, right? So you can adjust these input and output values and reflect the hospital administrator's policy decision in terms of how many beds should be allocated to the COVID-19 patients. Okay, click OK. The unit is going to be dimensionless. Click OK. All right, so now we are moving on to the next part where we are going to calculate the actual or adjusted fraction of hospital capacity allocated to infected symptomatics. Okay, so we're going to say adjusted so this is gonna be the normal fraction multiplied by this adjustment that's being made. Okay, so it's gonna be normal fraction multiplied by adjustment made. Still the unit's gonna be dimensionless. Okay, so now this is the adjusted fraction. Now we can actually calculate now how many beds would be allocated to the infected symptomatics by multiplying these two. Okay, so that's what we're gonna do. So the next step is a hospital capacity allocated to infected symptomatics. And that's gonna be hospital capacity multiplied by adjusted fraction. Okay, can move this around a little bit. Okay, as you can see, I rearranged the variable location a little bit so that we don't have overlapping arrows. Well, at some point we won't be able to avoid that, but I try my best. Okay, so that's the hospital capacity allocated for infected symptomatics. Okay, now the next part is where we calculate the staff burnout. So if this adjusted fraction of hospital capacity allocated to infected symptomatics continues to be higher than the normal fraction, that means hospital staff, they are overworking and eventually they're gonna burn out. Okay, so what that's going to do is that's going to lower the hospital capacity allocated to infected symptomatics. And that's exactly what's going on in some of the hospitals in US right now, because after years of having COVID around, Okay, hospital staff, they are burned out and they leave, and then there aren't that many people to work at the hospital. So there are some empty beds in the hospital, but then you can't admit patients because there are shortage of staff. So Alice model has that component built in. Okay, so that's what we're gonna do next. So first of all, we want to calculate the sustained capacity strain, and we want to embed the concept of delay, information delay here. So we will use the smoothing formula that we learned in module 5 here. Okay, I'm going to create a variable, average ratio of adjusted fraction to normal fraction of hospital capacity that can be allocated to infected symptomatics. Okay, that's a long variable name. And basically what we do here is we are comparing this adjusted fraction with a normal fraction, and for smoothing formula we need a smoothing time. So what's the time frame of data that we're going to be looking at? Okay, so here we need time to average the hospital capacity ratio. Okay, so this time constant will be 6 days. Okay, so if adjusted fraction is higher than normal fraction for, you know, some time, like a week, right, that starts to burn out staff working at the hospital. Okay, now the average ratio, this will be using smoothing formula. So you go down the list here, and then you're going to click smooth. Okay, and then the input will be adjusted fraction over normal fraction. That's the input. And then the smoothing time is going to be time to average hospital capacity ratio. Unit dimensionless. Click OK. Right? So this will be the input for our burnout effect, which will use the table function. Okay, so I'm going to call this burnout effect. And then Ali has a switch here which can adjust how much burnout effect that we want to incorporate into our simulation results. So we're going to create a burnout switch. So this switch is not just on and off, but you can actually change the degree of the burnout effect. Okay, and then the table function that we're going to be using will be F4. Okay, so this is what it's going to look like. Burnout effect has an input coming from here, average ratio. And then it's going to use the table function, F4. And then we're going to incorporate the switch. And that burnout effect is a multiplier that we're going to multiply to the hospital capacity. Okay, so that's the idea. Okay, now let's define the burnout effect. So let's go and define F4 first. We click that, and then we're going to turn this into lookup. Click as graph. Let's first adjust the X and Y axes. So X maximum, I'm going to change it to 4. Okay. And then Y maximum, I'm going to change it to 1. Right. And let's think about a situation where the average ratio is 1, meaning that adjusted fraction equals the normal fraction. In that case, there will be no burnout, right? So we don't really need to change the hospital capacity here. So this burnout effect will be 1, because when we multiply 1, it doesn't change whatever the hospital capacity here is. Okay, so it's gonna be 1. Okay, so if this average ratio is lower than 1, that means this adjusted fraction is lower than the normal fraction. And again, there is no burnout effect, right? So we wanna continue to have 1 in this range. So if x is less than 1, this burnout effect will be 1. It won't have any effect on this hospital capacity allocated to infected symptomatics. Okay. However, let's say that this average ratio is 1.5, meaning that adjusted fraction is 50% more than the normal fraction, and it's been going on like that for a while. Okay, then what's going to happen is our y-axis, it's going to be 0.6. So we're losing about 40% of our hospital capacity due to burnout. Okay, so then the next one is if this adjusted fraction is twice as much as normal fraction, then the burnout effect is going to be 0.4. Okay, meaning that we only going to have 40% of our hospital capacity. And then if this adjusted fraction is 3 times normal fraction, and it's going to be at 0.3. So in the current way, this table function is defined here. This adjusted fraction can go only up to 25% above the normal fraction. Having said that, as I mentioned before, policymaker can actually decide to allocate a lot more for the infected symptomatics than 25% over the normal rate. Okay, so in that case, you know, this average ratio can actually go way higher than 1.25, and that's why we are going with these higher numbers as the input. Okay, so when it's 4 times, we only get to have 25% of the hospital capacity. Okay, so that's what the table function looks like. Click OK. Select the unit, dimensionless. Click OK. Now let's go and look at the burnout switch. So far, let's just set it to 0. Okay, and then whenever we are running simulation, we can change this value. Okay, so just remember this is 0. And let's now figure out the burnout effect. Okay, so the burnout effect is going to be F4, and then the input value is going to be average ratio, right, that we calculated using smooth formula. And now we have to think about the burnout switch. So we're going to multiply this to the burnout switch. Okay, so current value of burnout switch, think about it, is 0. So then this whole thing will be 0. Okay, now then what we do here is plus 1 minus burnout switch. Okay, think about the first part. We are multiplying this F4 output with burnout switch, which is 0. So that part becomes 0. But the second part here, 1 minus 0 becomes 1. So the whole thing is 1. Right? So when burnout switch is 0, you don't want any burnout effect in your model. This whole thing will give you value of 1. And when you multiply this burnout effect as a value of 1, it's not going to do anything to this hospital capacity allocated to infected symptomatics. Right? However, let's say that we want full burnout effect. Then you're going to put 1 in the burnout switch. In that case, it's going to be F4 times 1, and then the second part will become 0. So you are taking in the full effect of F4. All right? However, let's say that you just want 50% of the burnout effect. Then you're going to put 50% here, 0.5. So you just get the 50% of the output of F4. And then you're going to add that to 0.5 here. Okay? So that's how Ali modeled the switch, so that you can go between full burnout effect to zero burnout effect, and your model will run accordingly. Okay? Really awesome formulation. So the unit is gonna be dimensionless. Okay? Now you're gonna multiply that to the hospital capacity. What you're gonna do is you're gonna do hospital capacity multiplied by adjusted fraction of hospital capacity allocated to infected symptomatics multiplied by burnout effect. Okay? So in this case, the unit's going to be person. So that's finally, after considering all these demand pressure and burnout, this is how many beds that are actually allocated to infected symptomatics. Okay? Now what we're going to do is now we're going to calculate whether that was adequate. Was all the people who wanted to be hospitalized got hospital beds? Okay, so now we're going to calculate a variable called hospital availability. So basically what we're going to do is we're going to calculate the hospital availability here. Okay. And basically we are comparing this, people who need hospitalization, with the beds allocated to infected symptomatics. That's what we're gonna do. Okay? So here we're gonna say, so the question here is the hospital available? Okay, so we're gonna be using if then else formula. So if you scroll down here, there is if then else. Okay, so if this, the capacity we have, is greater than infected symptomatic needing hospitalization, that means we have full hospital availability. So we're going to say if that condition is true, the value will be 1. Okay? If not true, okay, then the value will be hospital capacity allocated to infected symptomatic over infected symptomatic needing hospitalization. So let's say that you have 20 hospital beds allocated to infected symptomatics, but you have 100 people out there who needs to be hospitalized, then hospital availability will be 0.2. Okay, so that's our if then else function, and hospital availability is gonna be dimensionless. Why did we calculate the hospital availability? Because that's gonna have an impact on the recovery rate as well as the death rate. So those are the two last steps. Okay, so let's first figure out the recovery rate. So we need to create a variable here called effect of hospital availability on recovery rate. Okay, so and the function, lookup function, table function, we're going to call that F5. So hospital availability is our input with the F5. That's going to feed into the recovery rate. Okay. Okay. And another thing that we need to think about here is we kind of have two different paths. People who needed hospitalization then those people will be affected by hospital availability. So their recovery rate depends on hospital availability. But there are some fraction of these people who doesn't need hospitalization, right? Then those people won't be affected by hospital availability when it comes to their recovery. So you gotta kind of separate these people into two groups and only multiply this effect of hospital availability for those people who needs hospitalization. So what we want here is, you see that the fraction of infected symptomatic needing hospitalization, that also need to be factored in defining the recovery rate. Okay, so that's another arrow that you want to add. Okay, now let's go and define this F5. Okay, so it's gonna be a lookup, and you click graph. Let's first change the value, x maximum to 1, y maximum to 1. So if x is 1, that means the hospital is fully available, right? Then effect of hospital availability on recovery rate will be 1, because you don't want it to have any effect on the recovery rate. However, if this hospital availability goes below 1, okay, that's when things go bad. Alright, so I entered all the values here, and what you're seeing here is when the hospital is not available, then those infected symptomatics who needed hospitalization, if we have 75% of the hospital available, that means 25% of infected symptomatic needing hospitalization, they don't have hospital beds. It's gonna cut down the recovery rate by like 3%. Okay, click OK. Now the unit dimensionless, click OK. Now the effect of hospital availability on recovery rate, therefore, will be F5 with hospital availability, unit dimensionless. Okay, and then the recovery rate now is gonna be, you wanna modify the equation that you have. So remember that the people who's gonna recover is infected symptomatic population, and you kind of had to subtract people who are actually dying. So there are, you see that, two different pipelines, okay? And then the fractional death rate determine how many people go this route and how many people go that route, right? So out of people who go this route, now we have to figure out who needs hospitalization and who doesn't. Okay, so here we're gonna multiply that to fraction of infected symptomatic needing hospitalization. So that's the first group. So out of infected symptomatic population who's not gonna die, okay, some of them need hospitalization, and their recovery rate will be affected by this hospital availability. So we're gonna multiply that with effective hospital availability on recovery rate. Okay, now this whole thing is first group. Okay, so I'm gonna tie them with a parenthesis. Okay, now we're gonna add that to infected symptomatic population multiply by 1 minus fractional death rate. So these are the people go through the recovery rate pipeline, and you have to multiply that by 1 minus fraction of infected symptomatic needing hospitalization. So these are the people who doesn't need to go hospital. Okay, and this whole thing will be divided by average recovery period. Okay, I hope I got all the parentheses right. Sometimes it gets really confusing. Oh, here. I gotta say 1 minus. Okay, let's read it again. Infected symptomatic population multiplied by 1 minus fractional death rate multiplied by fraction of infected symptomatic needing hospitalization multiplied by effect of hospital availability on recovery rate. And we're gonna add this whole thing with infected. Let me just add a parenthesis here. Infected symptomatic population multiplied by 1 minus fractional death rate multiplied by 1 minus fraction of infected symptomatic needing hospitalization. And then we divide this whole thing by average recovery period. Okay? Alright. So that's that. And we are really at the last step, because now we want to create effect of hospital availability on death rate. And then the table function is going to be F6. Hospital availability will have an effect here. Let me move this around a little bit. And then F6 connected to this variable. Okay, and this will have an impact on the death rate. And also this fraction of people needing hospitalization will also affect the death rate, because only people who need hospitalization will be affected by hospital availability. Okay? Alright, now let's go and define the equations. So F6 in this case, turn it into lookup as graph. Okay, now this one is gonna look like this. First we change the maximum value of x and y axis. So let me explain what this is. When there is no shortage of hospital beds, okay, then it has no impact on the death rate, right? However, as we are experiencing, shortage of hospital beds, so if the hospital availability goes below 1, then we are quickly seeing a huge rise in the death rate. Look at this, the multiplier is like 4. So when there is no hospital beds, then it can actually increase the death rate by 4 times, right? And when there's only 75% of the hospital beds available for the COVID-19 patients, then it can actually increase the death rate by 1.4, meaning 40% increase in death rate. So what you're seeing here is this effect of hospital availability is way greater on the death rate than the recovery rate, which makes sense, right? So unit's gonna be dimensionless. Okay. Now the effect of hospital availability on death rate, that's gonna be F6 with hospital availability. Okay. And then the very last step, the death rate. Okay. Again, we have to divide this into 2 groups. Okay. So it's going to be infected symptomatic population multiplied by fractional death rate multiplied by fraction of infected symptomatic needing hospitalization. And those are the group that's going to be affected by hospital availability. So that's one group. Okay. So we can put them together. Oops. And we're going to add that to infected symptomatic population who are going through the death rate pipeline. So it's going to be fractional death rate multiplied by 1 minus infected symptomatic, fraction of infected symptomatic needing hospitalization. So this is the group that's not going to be affected by hospital availability. Okay, So we can put all of those in the numerator, and then we divide that by average time from symptom appearance to death. Okay. All right. So let's save the model. Now we are ready to run our module 7 base. Simulate. Okay. Now take a look at the what are some of the things that we want to check out. Let's see what happened to the infected symptomatic population. Okay, this is the infected symptomatic and susceptible population. Okay, module 7 and module 6. What you're seeing here is that we haven't really turned on the burnout effect. See what's going on with how many people are needing hospitalization and how many people are actually admitted to hospitalization. We can go to control panel and we can create a new graph, and this is and I'm gonna select infected symptomatic needing hospitalization. Okay. And then hospital capacity actually allocated for infected symptomatics. Okay, I'm gonna lock their scale. Okay, let's see. Display. So this is what's going on. So there are this many people that needed hospitalization, but they couldn't, okay, due to lack of availability. So, you know, that's the model that we built here. You can play with it. You can try out a lot of different scenarios. You can even run the simulation with changing this burnout switch from 0 to 1. Okay, let's see what happens if we change it to 1. Model 7 with burnout. Okay, simulate. And now if we go and check out the hospital availability, okay, this is the without the burnout, and this is with burnout. Okay, so it does have impact on the hospital availability. And then if we go to the okay, so with burnout effect, it kind of lowers the hospital availability, right? So that's what's going on. So take a look at this. This is hospital capacity allocated to symptomatics, and the blue line is with burnout, and the red one is without the burnout switch turned on. Okay. All right. So that's it for this module. Next module, we will actually go and add quarantining of infected symptomatic population. So as we go through these modifications, our model is becoming more and more realistic.